All right. All right. Really like today's lecture. I like the last half of it is probably one of my favorite lectures of the semester, just because we kind of get into some of the nuts and bolts of hypothesis testing in terms of what it is, what it isn't, what we can say, what we would like it to say, but in what it actually tells us, and sort of some of the traps that we fall in terms of sort of making interpretations about our data, the confidence that we have in it, and some of the problems that creates. But first we're going to go through, talk about distribution of means, central limit theory, probably covered in some of your early stat classes, but that you have probably, and sort of nothing against the sort of the undergrad stat class, but it was probably sort of in one ear and out the other, because that's not the level you're learning things at those early stages. But really, really want you to be comfortable and understand what's actually happening when we're running these inference tests. I'm going to talk about null hypothesis significance testing, criticisms that have been around forever and ever and ever that we just earmuffs to and ignore aren't things, but this has caused problems for our science, and recommendations. So up to this point, with the stuff that we were doing for z-scores before, what we've been doing is focusing on identifying the location and probability of individual values in a population of values, right? We're looking at a z-score, we say, okay, this person, Allison has a z-score of 2, what's the likelihood, what's the position or rank of Allison relative to the rest of the population, right? Which is kind of a slick parlor trick. We like that. Pull that out in sort of any party you're at, like people will be very impressed by sort of calculation you use it. You pull out that table, right? You'll be a hit. Problem is when we're doing actual research, rarely are we ever interested in sort of where an individual score lies. An individual score is just one score in a whole set of scores. Where Allison actually lands is of no consequence to me as an investigator, because I don't know you from Adam. Like, it does, you're just one observation in a set of observations, right? Sometimes, and again, I've sort of talked about this in sort of clinical work, right? Or sort of if you're working with that outlier, sort of maybe one individual starts to become relevant to where it falls. But really what we're most often worried about within the context of applied research, particularly means-based research, is making inference about sort of the means of a sample, right? So I've got not just one person, I've got a whole set of scores. And what I want to do is go through and sort of make some inference about sort of the average score in that sample. Because what am I using the average score in that sample as an indicator of? What does that average score tell me? What do I hope it tells me? What do you think, Gabe? If I take the mean of a sample, what is almost by definition what am I trying to estimate? Yeah, the mean of the population. I can't measure the population. What I've got a sample, and I can take the mean of that sample. And what I'm guessing, what I hope, or what I should be thinking about, is that this mean represents my best guess for the population estimate of whatever population that sample is drawn from. Okay. So the good, like we've been going through and taking and looking at, sort of assuming a distribution, looking at the probability of obtaining a specific from a distribution, we can take these same principles and extend these out. What we can start to do with some mathematical statistical theory is start to draw specific estimates of the likelihood or probability of obtaining a specific sample mean in a distribution of all other possible sample means that could be constructed from the population. So we're taking the same principles that we used with our individual scores, and what we're doing is that extending that out to making estimates and inferences about means, which is starts to become super, super handy with things. Okay. All right. So if we're looking at talking about the distribution of sample means, definition here is the distribution of means obtained from all possible random samples over a particular size that could be drawn from the population. Okay, so before we're working with individual scores, and sort of like our sort of normal curve, and those are all individual scores. when we're talking about the distribution of sample means, our distribution graph, each one of those values is represents a distribution of sample means. So each one of those values in that distribution is a specific mean that was drawn from a sample of individuals. Okay. So in practice, when we're doing things, right, there are functionally, in most cases, countless samples that could be drawn from a given population. I mean, there actually technically is an upper limit for this, but depending on the size of our sample, right? If my sample is everybody in the world or everybody in the US or all people who fall into this characteristic or group, an infinite number of samples that could be drawn with replication from that group, right? And so it's impossible to calculate all of those samples specifically. I really think of this theoretically. So if we took all of the on-campus students at the University of Wyoming, and we wanted to measure again, like the height of everybody, right? And we had samples of 50. Technically, there's a set number of students. There are a set number of on-campus undergraduates at the University of Wyoming, right? And we could get that number. We have contact information for all of those. And we technically could go through and sample all possible samples of size 50 from, let's say there's 6,000 undergrads, right? We could get every single possible sample of sample size 60 with replacement from that, but I don't even know what that number of samples would be. The number of samples of 50, even from a extremely small population like the University of Wyoming undergraduate students, would be massive, right? Take that, explode that into a population level, so like all people in the world, everybody in the US under the age of 18, everybody who exceeds an extroversion score of this, right? And so basically what we're talking about is like a functionally unlimited number of potential samples that could be drawn from the population, okay? People kind of following me in terms of what we're talking about here in terms of a distribution of sample means? Okay. Okay. So let's try this, okay? So we can't calculate all of these individually, but what we can do is we can fall on some math and some statistical theory to start to understand some of the properties by definition that will start to emerge from this distribution of sample means, okay? So let's take this as an example. Let's take it down even further. So Danielle, I've got a population of scores. I got 4 scores, okay? These 4 individuals, these 4 observations are all that I care about in the universe. Like these are the ones, right? And I've got scores of 2, 4, 6, and 8, okay? The mean of that sample is 5. What's the shape of that sample look like, Danielle? Yeah. How would you describe that, the shape of that population? Yeah, yeah. So how would, yeah. No. Like, yeah. Yeah, so we would say that this is sort of has high kurtosis, right? And I would call that like a uniform distribution or square distribution, right? There's actually, I mean, there's no sort of normal curve with that. It's just kind of a flat distribution there, right? So basically, I've got one person or one observation at each one of those 4 values, right? Is that a normal curve? No, it's not at all. No, that's fine. Up top. Lean into the fear. That's fine. Like be authoritatively wrong and just like go through. Like you weren't the only one. You just happened to be the one I called on, right? That's what you get for asking questions in my lecture. Good work. All right. So we've got 4 scores. But what I could do is, let's say I wanted to go through from this population of 4, I wanted to contribute a distribution, construct a distribution of sample means of sample size 2. Okay. And with these 4 scores, there are 16 unique samples that I could draw from that population with replacement. So my first one, I get the score of 2, put it back in, get 2, okay? Next one I get 2, I get 4, 2, 6, 2, 8, 4, 2, 4, 4. Like this is just going through all possible samples, right? So even with just 4 observations in my population, with sample size 2, I get 16 different unique samples that could be drawn from that population. Okay. People following what I'm doing here? So to just, well, I mean, kind of probability, but say Tell me a number tell me a number in this observation, Mandy. 7. Well, no, actually, yeah. So 7's not there, right? So 4. Okay, cool. So I got 1, 4, and then I pitch 4 back in. Give me another observation. 2. Okay, so I've got 4 and 2. All right. So now give me another one. So that's one sample. 8. Okay. And what else? And 6. Okay, that's another sample of 2. We would keep doing this and doing this and doing this and doing this until we had all possible samples that could be drawn from this population. Yeah. So I mean, so if I went through and 6 on the first draw and 4, and then on the next one I draw 4 and then 6, is that a unique sample? No, it's the same people, right? So what we're doing is saying with replacement, all possible samples that could be drawn from of size 2 from this population. And if we do that, this is what it looks like. Yeah. With replacement is important. It's part of the statistical theory, right? Anytime we're doing random samples, it's always the assumption with replacement that someone else could get in. Now, when we're actually collecting our data, we don't want to get the same dependencies going on, but from the perspective of statistical theory and sort of this concept, it's always with replacement. Yeah. The sample of 2, I got the same person twice, and that's going to happen, right? Mm-hmm. Yep. 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 Haley. Okay. Okay. So are people seeing kind of sort of what's happening sort of with what we're doing here? Yeah, Mesa. You have 2, 4, and 4, 2. Yeah, I guess that's I guess with the replacement. Yep. So good in terms of catching that. Yes. So it's a different, I guess. Yeah. Order does matter. Yeah. So we got 2 and 4, and then 4 and 2 are both in here, but that's within this context is considered a unique sample. So again, if I randomly draw 4 and 2 again, then that wouldn't be unique because I've already got a 4, 2 in there. So yeah, so it's it goes back to that with replacement piece of things. Okay. But what happens if I go through and I do this? So there are 16 different possible combinations. I sort of in this scenario order counts, right? What I could do is then walk through and calculate the sample or the mean of all possible samples of 2. Okay. And if I, right, obviously the mean of 2 and 2 is 2, and 2 and 4 is 3. So you're just going down through and calculating the mean of these 16 samples. Okay. And then if I go and take the mean of all possible samples of size 2 that could be drawn from this, and I create a histogram of the means that I gathered here, what's happened to this distribution? Now it got all nice and normal, right? Now we've got a nice mean median mode is all sort of right there in the center, and everything starts to pan out. Okay. And so what we say when we're going through, when we're looking at a sampling distribution, right? And a sampling distribution, again, this is an important definition. A sampling distribution is all possible samples of size X, whatever it is that could be drawn from a population. Now, this is a small set with 4 scores in the population and sample size 2, but even at that level, this is still behaving the way that we would expect the sampling distributions to behave. What we know is that the distribution of sample means start to pile up around the population mean. Okay. Remember here in our population mean is 5, right? We go through and take a look at the mean of our distribution of sample means. What's the population, or what's the mean of the distribution of sample means? It's 5, right? And so what we know is that the mean of the sample means will be equal to the population mean. Okay. We know that the distribution of these sample means will generally form a normal distribution. There are a couple of things that start to sort of influence how quickly we'll get to sort of that nice normal distribution. And then what we can do with the distribution of sample means is we can start to answer questions about the probability or likelihood of selecting a random sample having specific characteristics based on sort of some assumption about the population. Okay. So again, if we go through and take a look at our distribution of sample means, we can say, what's the probability of selecting a sample having a mean greater than 7? We got 16 scores. Johnny, what's the probability of me randomly selecting a sample of 2 with a mean that's higher than 7? Okay, one of those boxes. And so someone works with the probability. What is it, Mandy? Oh. Okay. So is it likely, if this is my population here, is it likely for me to randomly select a sample with replacement that gives me a population mean or a sample mean of 8? Something higher than 7? No, that's a 6% chance. Can it happen? It can happen, but it's very unlikely, right? And so this is what we're doing with all of our inferential statistics, is we're starting to try and understand something about the an assumed population based on sort of the likelihood of obtaining a sample of certain characteristics. Okay. People sort of at least sort of kind of grasping some of the stuff that we've got sort of going on with this. Yeah, no. Yeah.
So if we're talking like
Yeah.
These are all the people then you just then it's just gonna be represented.
This is a much simplified example.
Okay.
If I only have 4 people in my population and I already know what their values are, then I don't need to use statistics. I can just say, this is what the population looks like, right? Because remember, anything that we're doing with inferential statistics is always trying to infer something about a population, right? And so if I already know the population, then I don't have to worry about statistics, right? But for this, right, so let's say that same principles here in terms of, let's say we have 6,000 undergraduates on campus, right? And I want to take average height, or I want to look at I want to know something about the average height of students, undergrad students on campus. Roping 6,000 undergraduates and getting a height on them is probably hard to do, right? But conceivably, what I would want, if I wanted to actually sort of know what that population value was, I really don't have to get all 6,000 people. What I could do is I could start just randomly pulling samples of 50, samples of 25 even, right? And just get 25 kids, heights, 25 kids, heights, 25 kids, heights. And as I started to plot those, the means of those samples of 25, what's going to happen is it's going to start to do that pretty quick. And what I know is that what I can do is start taking the mean of the distribution of sample means, and the mean of the distribution of sample means mathematically is equivalent to the population mean. Now I'm still going to have some variability in there, right? Like unless I sort of go through and do, but I can start to get very, very, very close to what the actual population mean is without actually accessing the full population. And this is kind of the heart and soul of what we're doing with our inferential statistics. Does that help? Okay, good. No. You're never bothering me. These are always, because you know what? Other people are having the same questions too. So thank you. Yeah, Mandy. How many in this distribution are grade 5? Yep. 6/16, and that's a probability of randomly selecting a sample, having a sample mean greater than 5 out of this, right? And so what's the probability of that? That's actually not too bad, right? Like that can happen. What we start to do, and when we get into sort of our the rules of our interval or our inference tests, is we have a hypothesis. We have a null hypothesis about the characteristic. We have a belief that we state that says the population value is X, right? So if I go through, if the population value of X, if that's true, and I go through and I get a sort of sample of a certain size that's quite different from that, what I can start to do is saying, assuming that this is the value of the population, what's the likelihood of me obtaining a sample, random sample with this characteristic or larger, right? And then we start to use that to start to make inferences about the likelihood of the null hypotheses. Okay. So this distribution of sample means what's known as the central limit theorem. I'm sure everybody's heard this before. You might not have sort of kind of internalized what this actually means. But the central limit theorem says that for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means for sample size n will have a mean that's equal to the population mean and a standard deviation that's equal to the standard deviation of the population divided by the square root of the sample size, and will approach a normal distribution as n approaches infinity. Okay. So there's a lot of stuff to kind of unpack with this, right? So let's first talk about the shape, okay? What we know is that the distribution of sample means starts to approach a normal curve under either of these two conditions. One, if the population from which samples are drawn is normal, right? So if I'm looking at something like intellectual ability, right, which we know kind of so it falls on sort of this normal curve. Even if I'm sampling relatively small samples, like say sample size 10 or something like that, even with samples of 10, that distribution of sample means is going to start to hit, start to develop a normal curve very quickly, because what I'm sampling from as a normal distribution, right? So if I'm sort of even, let's say I go through and I grab 10 people, right? And I sort of look at their IQ score. Those of you in Tara's class, what are most of those scores going to be very close to? About 100, right? Kate, are they all going to be 100? Am I sometimes going to maybe very high or very low? Yeah. Am I maybe going to, on a very, very rare occasion, get a whole cluster of people who are very high or very low? Yep. But on average, most of those folks are going to sort of, those samples are going to fall right on around the mean, sort of right around 100. And then so we start to get samples that are increasingly unlikely, but they're going to be there, right? So if the population for which samples are drawn is normal, we start to see this shape develop very quickly. Or if our sample size starts to get large. Now, this is around 30 or more, and this is old school statistics. What people will talk about is a large sample size, any sample size larger than 30. That's not true. Like maybe in the 50s, like we've sort of developed a different relationship with sample size and things along those lines. But mathematically, what we'll start to see is at sort of that level, central limit theorem takes over pretty quickly, and we start to see pretty normal curves, okay? So let's say in this example here, we'll say that this graph represents random samples of adult height of sample size 100, right? So if I were to, through the US Census, right, and just go through and take random samples of adults from the US and measure their height, right? And I'm taking samples of 100 with replacement and going through, and I went through and started to plot those heights very quickly. Height is something that's distributed on a normal curve anyway. We would very quickly start to see this turn into, the distribution of sample means turn into a normal curve. Are people comfortable with shape, like where this starts to emerge? All right. Other thing that we know based on central limit theorem is information about the central tendency. We know that the mean of the distribution of sample means, so this is going to be the average of all possible sample means of a given n, that's going to equal the population mean, okay? So here, if we're looking at sort of this distribution curve, we see that the population mean 60. And then if we take a look at the mean of our distribution of samples, what we refer to as the expected value of the mean. It's also 68 inches. It falls right on there. And this expected value of the mean, this is just as the mean of a distribution of sample means, and it's equal to the population mean. Okay. Not the I mean, it's equal to the population mean. We don't call it the population mean though, because the population mean is something that's unknowable. But the expected value of the mean, we can start to measure that with resampling procedures, right? But what we know mathematically is the expected value of the mean, or the mean of the distribution of sample means, is going to be equal to the population mean from a theoretical standpoint. Following this. All right. Finally, variability in the distribution of sample means. Okay. The standard deviation of this distribution. So we've created this distribution of sample means, right? We've got all possible means of size 100 that could be drawn from the US population in theory, right? And we go through and we take a look at that distribution of means. That distribution of means is going to be symmetrical. The mean of that distribution of means is going to be equal to the population mean. And the standard deviation of that distribution is going to represent our standard error, okay? Standard error is the standard deviation of the distribution of sample means. We talked about this before when we're talking about calculating confidence intervals. It's just going to be the population standard deviation divided by the square root of the sample size, right? So here we have a population variance or population standard deviation of 6 inches. Standard error mean is going to be 0.6, okay? And just if I go through and I say standard error of the mean is equal to sigma or square root of n, right? That gives me standard error of 0.60. Okay. This is a critical slide. I want you to like deeply internalize this, because standard error again is a critical statistics that we're going to. Our standard error in a number of different ways, and I would encourage you to think about standard error in a number of different ways just to increase flexibility. We can think about standard error as providing an index of how much difference is expected from one sample mean to the next. Okay. Again, all the same things that we could say about a standard deviation apply here, because the standard error is just the standard deviation of your distribution of sample means. So I could say, if you give me a standard error in this scenario is 0.6, right? This tells me if sample size 100, if I were to go through and randomly select people from the US population and sort of like say I've got a couple of different samples, Olivia, how much would, I don't know anything, or you don't know anything about these two samples that I'm holding behind my back, but if you had to guess, how much of a difference would you say there is between those two samples? If you the standard error of what's that? Give me a guess. Okay, kind of close, right? So what it was, if this is height in inches, what does standard deviation or standard error of 0.6 represent? To deviate from the mean by 0.6 of an inch, right? So if we're talking about this in very literal terms, this is 0.6 of an inch. So given a standard population standard deviation of 6 inches, right? And if I'm taking samples of 100, and if I know my standard error is equal to 0.6, what I'm literally saying is I expect any two randomly selected samples from this sampling distribution to differ by a little over a half an inch, right? What's the level of precision on that? That's pretty good, right? That's pretty good. So again, thinking about standard error as the extent to which I would expect things to start jumping around from sample to sample to sample, okay? So again, going back, Olivia, if my standard error is 0.6 and I have a sample that I collect, and then you're looking to collect another sample from the same population of about 100, are you expecting yours to be pretty close to mine or maybe far away from mine? Pretty close. Does it have to be? No, it doesn't. You could end up with some, but on average, it's going to be pretty close because we've got a large sample and we're working with some pretty precise stuff. Yeah, Haley. Yeah, Yeah. Mhm.
Uh,
Nope. I'm saying on average.
on
If we do this over and over, I'm glad you brought that up because Haley, your sample be anywhere from the very, very far end or the very, very large end. Okay. Okay. Two things. One, thinking about the sampling distribution there, right? Like, so there could be sort of in all possible samples of size 100, there are going to be some of those samples where you just happen to sort of collect people who are on maybe the shorter end or the smaller end. That's going to be out there on the side. It's going to be incredibly unlikely, particularly with the likelihood of randomly selecting 100 people who are all extremely small is very unlikely, but it's not impossible, right? So in terms of like in thinking about sort of Asian Americans, people from sort of different cultural backgrounds and sort of things along those lines. So certainly thinking about some differences in sort of average height and things along those lines. But if these are all folks from the U.S., like they're all in the mix. They're all part of the thing, right? And so they're all relative to be getting sampled. What's the big thing though? What's the big sticking point for why what Haley's talking about shouldn't apply to what we're talking about here? Yeah,
oh,
yeah, exactly. The idea is that if you were to do that, then you rules. Now all of them are no longer any good because what you've done is you've not collected a random sample. You've gone through into one community and collected a bunch of people because it was convenient, right? Now all of a sudden we don't know where your stuff is going to land, right? Yes, yes. And this is the thing to remember is because we talk about these statistical procedures and it's all based on a perfect world. In theory, in a vacuum, right? If all these things hold, these are the things that this is the way things should behave. But this isn't how we actually do applied statistics right now. So the option is just don't do statistics at all, which seems extreme. We can still do them. And a lot of times things will continue to hold, but things like generalizability, sort of all these other things, it starts to degrade on the level of my confidence in my inferences, right? And so I need to start maybe being a little more judicious in terms of my interpretations on what's happening, okay? But if I go through and thinking about standard errors, an index of how much is expected from one sample to the next, on average, if I just took two samples and put them behind my back and had you guess, and I did it again and had you guess, and it didn't get in and have you get, what would be mathematically, what's your best guess every time, Abby? 0.6. Is it ever going to be exactly 0.6? Probably not. But if we go through and average the actual discrepancies across an infinite number of things, the average discrepancy is going to be 0.6. Okay. And so this is the level of uncertainty sort of on a large scale. This is what will happen mathematically if we're playing by the rules. But on an individual level, it's very, very difficult to know sort of where I just went through and grabbed a random sample. Where do I think it's probably from? Probably all right here. Is that where it's going to be from? Not necessarily. It could be anywhere. And so this is why it's so important to know about my research area, right? Sort of know what's been going on, like be aware of other measurements, because then if I get a mean of 54 inches, I should recognize that that's a strange thing and not something that makes a lot of sense given what I know about this population. That doesn't mean I did anything wrong necessarily. Probably it means that I sampled from a biased sampling set, but I can also just randomly get that, right? So think there as one way of thinking about this is how much difference should I expect from one sample to the next? If I'm using large samples and that's driving my standard error down, I would expect on average, I'm probably going to be pretty close across repeated samples. Yeah, Johnny, do you have a question? Uh-huh. Yep. Which is what our standard deviation is. Standard deviation of any distribution is just the average distance of two randomly selected scores from one another, or the so we go through and think about standard error as a measurement mean is likely to estimate the population mean, right? With sample size 100, I expect on average that any randomly selected sample from this distribution will fall about 0.6 of an inch from the sample mean. Does that mean that all the samples that I collect will be within 0.6 of an inch? Absolutely not. I'm going to have some that are way above, some that are way below, some that are kind of centered around the middle. But on average, across all possible samples that could be drawn from this population, on average, they'll be about 0.6 of an inch away from the sample mean. Okay. So again, it doesn't guarantee that it's within that bounds, but on average, that's what things are going to look like. And so if I'm thinking about how well is my sample to likely estimate the population mean, it starts to give me a beat on sort of precision accuracy, and it's driven mostly by the sample size. Okay. So we can think about this as a measure of precision or error. We can also talk about this as sort of the difference between the sample mean and the population mean in general for the distribution of sample means. Again, that's not to say that my sample is only 0.6 of an inch away. But if you had to ask me how far away my sample is likely from the population mean, I would say, I don't know, probably about a little over half an inch, maybe, you know. I don't know that, right? But this is why should accumulate, like we know next to nothing from one study. A single study tells us virtually nothing about anything. I mean, it tells us a little bit about something, right? But this is why it's so important when we're going through and drawing our estimates and things like that to look at the research to ask plausibility, like, does this make sense? Is this representative, right? Because again, we're hoping and sort of, boy, if I had to bet whether or not where your sample is going to lie, I'm going to guess right here, but it could be sort of in either direction, right? We just don't know if all we have is just this one sample. Okay. All right. Questions about standard error? Kind of feeling sort of start. I mean, this is kind of some heady conceptual stuff, but I would sort of focus on this, spend some time with this, and sort of go through. And honestly, okay, like I don't hope your weekends are free because this is going to be exciting stuff for you all. This link up here. All right. What I've gone through and done, this is me working in SPSS with a sample, with a whole bunch of scores, and like literally just walking through and sort of drawing random samples from that and going through and calculating those and then doing it again. And like the whole video is not me, just you don't need to watch me draw 100 different samples. But like I sat down and actually went through just as an empirical demonstration, had a set of like, I can't remember, like 500 scores, and then drew samples of sort of whatever. And then just did it again and again and again and again and again and use that to build a sampling distribution. Not a magic, like you can see, like if you do that, like this will happen very, very quickly as you start to go through and do this stuff. Okay. And even if you're using data that's very, very skewed, right? So I just went through, created a set of scores that had a certain sort of level of skew, and so super skewed. But even if I'm sampling scores from a skewed data set, if I got a big enough sample, the actual population data may be incredibly skewed, but the distribution of sample means is just going to go straight normal very, very quickly. Okay. Because even with that skewed set, where are most of my observations going to be if I'm grabbing samples of 100? Let's say here's my distribution and sort of my right. And let's say this is a characteristic like, I don't know, second law folks, like psychopathy or something like that. Like hopefully people are going to be sort of way down here, but you're going to get some people who are sort of out there, right? That's very clearly not a normal distribution. But if I start repeatedly taking large samples of size 100, where's almost everybody going to fall? Probably right here, right? Now, am I going to get some scores that are way out there? Yep, I sure am. Well, what's going to happen? My distribution of sample means is still going to go normal so long as I'm using sort of large samples from that. Okay, because you say the mean of this distribution is X bar here is going to be equal to mu. So those two will be the same. Okay. So again, like all of our sort of inferential statistics are predicated on sort of these sampling distributions and sort of the expectation that that's going to follow certain characteristics. Okay. So again, if you're having, if this isn't clicking, again, that's 100% makes sense to me. It's a hard kind of thing to wrap your head around. I'll go through and send you, just because this is such an important thing. I'll post a handout that kind of walks through verbally what's going on. And then again, it might seem lame, but that video is pretty cool. Like if you actually do this, it starts to fall in pretty quickly. You know, I see people looking at me and he says skeptical, like you're going to have a wild time. Like pour yourself a drink, right? Like just sit down and watch the show. It's pretty good. Okay. All right. So factors influencing our standard error. Population standard deviation obviously is going to go through. If this is our formula, population standard deviation is going to impact our estimates of standard error. Standard error is going to decrease with the population standard deviation, but the big driver is going to be sample size. Okay, based on the law of large numbers, the larger the sample we get, more likely it is that sample is going to be close to the population mean. Okay, so if I've got a distribution of sample means that's collected from small samples, I'm going to have a big standard error. And so what's that distribution going to look like in terms of spread variability? It's going to be pretty spread out, right? As I start to increase my sample size, as my standard error starts to decrease, I'm still going to get some spread, but that spread's going to come in a lot tighter, right? Just because my samples are bigger, they're going to be more representative of the population. I mean, they're going to jump around some, but to a much less degree than if I'm working with a smaller sample size. Okay. And so if we look at this for standard error, if we hold a standard deviation constant, okay, and then just look at what happens graphically as our sample size starts to increase. Yeah. What was the last part of that?
Just like, is there ever point? Like
Yeah.
stop collecting?
Yeah. The question being like, is enough enough? Right? Do we always need 1 billion observations? That's a good question. And so in general, and particularly for certain types of things that we'll want to do, particularly like correlational analyses and things like that. And if we start getting into like SEMs and things like that, they're just large sample estimators. And so bigger sort of coefficients are gonna be better. But if we take a look at what happens here, like sort of in means-based scenarios for a standard error. So let's say standard error of the mean, right? At some point, we just kind of get asymptotically flat, right? Like, so if I've got, in terms of standard error, if I got 40 people, gains that I get from going from 40 to 100 are pretty minimal relative from a sample of 10 to 25 massive gains, right? And so this graph, this is kind of where that idea that large samples or samples of size 30 or larger, if we go through and we're like 30 is at, we can't, and this is all like semi-arbitrary, right? But like sort of kind of old school rule of thumb, when people say, oh, sample size of 30 is large, is because like once this really kind of flattens out. You continue to get gains. And if we're looking at like regression-based models and stuff like that, particularly if we're looking at interactions or small effects, really want to have sample sizes that, like if you can get 300-400 people, that's awesome, right? But for a means-based analysis, yeah, you kind of, and then you're just wasting resources, right? Now, if stuff's coming in for free, you got it, why not take it? It's going to increase your power. But if you're spending time and energy and resources, it's an effortful process to go through. This is where we go through and run power analysis and say, okay, sort of like, what is the sample size I need to reasonably detect the effects that I'm hoping to detect? Okay. Other thing too is we'll get into this when we start talking about type 1, type 2 errors, and what we're actually doing when we're looking at running these statistical analyses. All of our analyses, all our hypothesis testing is testing whether or not something is exactly zero. If I get enough people, it's never going to be exactly zero. I'm always going to reject the null hypotheses. And then we get another sort of possibility of overpowered studies, which can be problematic if I'm not being careful and thinking carefully about what I mean or what my data is telling me, sort of what the point estimate looks like relative to comparison values and things along those lines. So yeah, you can have too many people, and sort of certainly you hit a point where, like, yeah, you can calm down. You don't need to keep sort of collecting things. And from sort of depending on what you're doing, if you just ask people questionnaires, fine, whatever. But if it's something that's costing people time, energy, and effort, maybe putting people through stress to go through and capture some stuff, ethically, you're like, I don't know, do we need to just keep grabbing people to grab people, or is this something that we could cut it off? Yeah. Does that help, Jalen? Okay, perfect. Okay, so if we're doing this, if we're just sort of conceptually thinking about distribution of sample means, we've got a number of, if we think about the black line as sort of the population, right, that we're looking at, and then we've got sort of a blue, a green, and a red in here. Mesa, which one of those curves, those dashed curves, is associated with the largest sample, if those represent distribution of sample means? Sample size goes up, what happens to my standard error? Goes down. And what does standard error represent? Give it a guess. I told you there's one wrong answer in this class, and it's I don't know. So what is standard error? What does standard error tell us? Okay, yeah, so it's a measure of spread, right? And so which one of these, if sample size goes up, what happens to standard error? Standard error goes down. And if standard error is a measure of spread and variability in the distribution of sample means, which one of those curves is associated with the largest sample size? The blue one, right? And the red is associated with the smallest sample size, right? Got is this, it doesn't really look like a normal curve, but it's kind of the normal curve of actual sort of, this is what the population looks like, right? And what we have here is three different sampling distributions. The red is the one with the sampling distribution corresponding to the smallest sample because it's got the most spread. The blue with the least amount of spread, right? But we can see with the largest sample associated with the smallest standard error, things are starting to come tight, right? Sample size gets smaller and smaller. Our sampling distribution starts to get sort of more and more spread out. There's more variability to that. Okay, so this is just a way to go through and take sampling distribution superimposed on the actual population distribution. That line there is just sort of ability scores and sort of what those look like. The dash are representative of sampling distributions and kind of what those are looking like there. Okay. Questions about that? Okay, so pulling this all together, we're actually working up to this point. We've talked about three different distributions. We've got a distribution of population scores. This is all scores in a population. Okay, this is going to have its own shape, mean, and variability. Like these are all, we never directly observe the population. The population is kind of like the mean, standard deviation in the population. These are all, they're numbers that sort of exist in theory, but something that we'll never actually observe in almost all cases. But if we're thinking about a distribution of population scores, we've got a mean, and standard deviation, variability, shape, right? Then we've got a distribution of sample scores, okay? This is, I can't observe the population directly, but what I can do is I can go through and I can pull a set of scores that I'm hoping are going to be representative of that population, okay? This sample distribution is going to have its own shape, mean, and variability. And I'm going to have a distribution of sample means, right? Distribution of sample means is this sample means from all possible samples of a specific size that could be drawn from a population. It's going to have its own shape, mean, and variability. Okay. But take a look, we can say, like, again, just, I don't know, achievement's an easy thing to do because it's like, okay, it's bell curve, whatever. So we've got in the population our distribution of scores, right? And so we know that that has a population mean of 100, standard deviation of 15. Now I can go through and pull a sample of individuals, right, from the overall and representative. But even if it's a perfectly representative, perfectly random sample, that sample is going to have its own sort of shape, mean, standard deviation. Okay, so my population, I know my population mean is 100. Here, mean of 102. I'm close, but it's not exact. What do we call that difference between what the population is and what I actually observed in my sample? Good. There we go. Sampling error. For the win. For the win. Sampling error. Sampling error is just the discrepancy between the population parameter and my sample statistic. Okay. but Katie, yeah. So with standard error, with a sample size of 30, should I expect my standard error to be sort of big or small? Probably pretty big. 30 is not a big sample, right? I mean, it's a fine. Giving achievement tests is a lot of work, right? And so like there's cost to going through and doing this, but it's not super big, right? But if we want to know what it is exactly, I go, I want to calculate that for me. Everybody needs to have calculators at the ready. Do arithmetic at the drop of a hat. We got Johnny? 7. Okay. So, to your point, right? We know that with a sample size, we already know the population standard deviation. I'm expecting that on average, any sample that I randomly select of size 30 should on average be about 2.7 units away from the sort of a different replication on average. I expect my sample to be about 2.7 points away from the population mean, and actually what we've got within the bounds of what we would expect just based on sampling error, right? My population mean is 15, stat and is 15.6. So we've done a pretty good job. Like our sample is behaving exactly like we would expect based on statistical theory. Is that a normal sample? Sample looks kind of weird, right? But so this is behaving exactly like we would expect it to based on so how things should work out. So we've got our population and then distribution of sample. Distribution of sample means is going to be all possible samples with replacement that could be drawn from sort of whatever we've identified as our population. And as we go through and do that, we see a very, very sort of normal curve. So everything sort of pans out. And we know that the expected value of the mean for that distribution is going to be equal to the population mean. The standard deviation of that distribution is going to be equal to population standard deviation divided by the square root of the sample size. Everything kind of locks into place here. People kind of comfortable with sort of these three distributions, kind of what they look like and how they behave in theory if we're playing by all the rules. Okay. I don't know. Maybe it's just because I teach this stuff and I like this stuff, but it's really, really super cool that this just works out the way it does, right? I mean, it falls into place. Now it's all, again, highly predicated on I should, or trying to get as close to playing by the rules as I can, right? But yeah, the fact that this actually works out, and again, which is why I was so pretty jazzed about that distribution of sample means video, is I just sort of I gave her a shot and it turns out the way it should. So, okay, let's do this. Come back at all right, 3:35. Give you 10 minutes. Come back. You're ready to rock and roll, and we'll jump into sort of more stuff. Let's jump. All right. So thinking about distribution is why this is spending half of class understanding what's happening with this is, again, the whole reason we go through and do this and sort of trying to harness identify very specifically the probability of detecting that has certain characteristics based on an assumed model. Okay, and that assumed model, there's a lot of stuff that goes into this idea of assumed model. But basically, if we have some assumption about the population from which we're sampling from, what we can then do is say, okay, if that's true, what's the probability of selecting a sample with mean M, assuming a normal distribution of means? Assuming we have a normal distribution of means with this sort of level, sort of whatever we've got under our null, we're saying we can very specifically calculate if this is true, then what's the probability of getting a sample with the characteristics that we're seeing here in hand, okay? And so what we can do is we can start calculating z-scores for sample means. Exactly the same way we went through and calculated z-scores for individual scores. All we're doing is we're taking our sample mean, subtracting what from our assumed population mean, and dividing it now instead of by a standard deviation by a standard error, okay? And if we do this, now we're getting a z-score, but this z-score is a test statistic, okay? And what it's going to do is it's going to give us an opportunity to go through and start to calculate the likelihood or the probability of assuming this is the characteristics of the population, the likelihood of obtaining a sample having these characteristics or those that are more extreme. Okay? So here in terms of practical example, so we say SAT scores have a normal distribution, mean of 500, standard deviation of 100. What's the probability of selecting a random sample of 10 students with a mean SAT score less than 440? Okay. We can calculate that very, very quickly with this. And I can tell you the exact probability of pulling randomly sampling 10 individuals who are going to have an SAT score of less than 440 based on the principles and sort of the stuff that we've gone through and talked about. We could also go through, let's say, what's the possibility or what's the likelihood of selecting a random sample of 75 students with a mean less than 440. Under these two scenarios, which one of these, gentlemen, is going to be most likely? Am I going to be more likely to get a sample mean that's less than 440 in the first scenario or the second scenario? So if we want to think about this, we know that SAT scores have a normal distribution in the population, mean of 500, a standard deviation of 100. Okay. So we want to know what's the probability of selecting a sample of students with a mean SAT less than 440 if it's a true random sample. Okay. No, to talk about it. Love where your head's at with this. Only thing that I would go through and provide a correction on this. As my sample size starts to get bigger, what happens to my standard error? Goes down, which means in terms of variability of my distribution, what happens? it comes in. So with that, which one of these is it's more likelihood, in which scenario is it more likely for me to get a sample 440 or taking that into consideration? The 10 students, right? That sampling distribution is going to be much, much more spread out, right? And so you're exactly right, and your head's in exactly the right place that, yeah, with only 10 students, it's probably really unlikely for me to go through and maybe capture some of those really low scores or really high scores for that matter. But if I do, only 10 people, that really starts to drag things down. And so if we're looking at the distribution of sample means, we just have much, much more variability in that distribution of sample means in scenario 1 versus scenario 2. Scenario 2, that's really starting to tighten things up. 75 is pretty good. My standard error is going to be pretty small. It can happen, but it's much less likely because I'm getting a much better and more representative sample with 75 students versus 10. Okay. Thank you for working through that. That's fantastic. People understand sort of why this plays out. Mandy, are you kind of seeing why this is how we arrived at that? What's that? No. Yep. Yeah. And so it's possible in both of these scenarios, but much less likely when we have a bigger, more representative sample versus the smaller sample. We just get a much bigger spread in terms of possible mean values for those. Okay. All right. So all this is in the service of trying to interpret patterns of data, right? There's a number of different sort of ways when we see patterns in the data or differences and things like that, a number of different sort of things that it could mean. One, some pattern is caused by some systematic factor that's reflective of an actual population sort of effect, right? Like this population is in fact different than that population in terms of their mean values, right? They're literally different. And when we go through and sample from population X and population Y, we see difference in those samples. And the reason we're seeing differences in those samples is because those samples are representative of populations with different means. And so what we're seeing is an effect that's reflective of an actual phenomena out there in the universe. But we can also have patterns, and so sometimes they're going to be due to just chance fluctuations and not representative of an actual effect. Okay, I've got population X and population Y. Population X and population Y actually have the same means, or a mean that's very, very close to one another, right? But I go through and I sample from X and I sample from Y, and maybe I get sort of a pretty big difference between those means. Well, does that mean represent what's actually going on in those two populations, Lindsay? Not necessarily, right? It's just random stuff, right? I've got population X, population Y, right? The means of these two distributions are functionally equivalent, right? They're not exactly zero, but they're sort of about as close as it gets. But what ends up happening through no fault of my own, just because randomization happens, right? It's here, a value of Y, it's in my sample, and now all of a sudden it looks like I got a big difference, right? In fact, there's actually nothing going on with this, right? And so here we can start to have, and particularly when our samples are pretty small, what I can do is I can start to find differences that don't actually represent true differences. The differences in my means look like the suggestive of a difference, but in actual fact, I'm just happen to get sort of different things. I could also pull a value and an X of here. Now what's happened to my inference? Now we're in the exact opposite direction, right? Just as easily, right? And so the things that we're seeing, the differences we're seeing in our samples can be due to sort of actual things that are going on in the population, or it can be just sort of just happening at random from where we go through and grab stuff, okay? We can also see patterns that are a result of systematic bias in the methods or violations of our underlying statistical model. Haley, when you talk about like, oh, I went through and sampled all my people from a very specific community, and then I'm saying like, oh, look at this, like I've found something new or different, when in fact it's not botched with your methods, right? You've gone through and done something, but it's not consistent with your underlying, the assumptions of your underlying model. And so now you're getting a difference, but it's not a difference that reflects something that's actually going on in the population. What we've got is a something that's due to a method effect, right? Oh, and what happens? What happens? We go through and we violate our assumptions, and we sort of go through and we get stuff that doesn't follow the rules that we've set up in terms of our distributions. Oh no! It's paranormal. It's scary. We don't know what's happening. We can't explain it. We can't explain it. We don't know how to account for it. We've got a distribution that doesn't do what we want it to. All right. So this whole process is part of our null hypothesis testing. Okay. What it is, it's intended to provide a set of procedures start to go through and separate sort of what actually sort of evidence to suggest actual population effects versus stuff that sort of maybe sort of better attributable or easily accounted for by just random fluctuations in our sample data. Okay. So again, the goal with this is to try and tease apart population-based effects and associations from just random fluctuations in our data, right? But there's no statistical test that will tell us if we've got garbage methods, right? I can't run a test to see like, oh, did I do a good job running my study, right? Data is just data, and all data is going to do is it's going to sort of, so we can plug it in, do whatever we want. It's sort of incumbent on you to be thinking carefully about methodology. So what did they do? How is the data collected? Are the constructs that they're reporting really reflective of the things that they think that they're measuring, right? And so again, we have to always go through, and it's not just about sort of getting pull down menus and SPSS, it's about thinking carefully about methods, what the assumptions are, and whether or not the data are likely to have met that, okay? Again, there's no statistical correction for garbage methods. Like if you've made a serious error in terms of your data collection, that's just kind of what we got to sort of live with it or try better next time, okay? It came out of nowhere, like you weren't expecting it. I did. That's you sort of you just didn't see it coming at you. I caught you off guard, right? Because it came out of left field. All right. So if we're thinking about our null hypothesis. Again, this is our procedures used to try and make some inferences about some unknown population value. Okay. So in this situation, right? So let's say we've got a population of rats, right? And these are sort of, anybody done rat research or sort of animal research, sort of neuroscience stuff? Andy, Allison, okay. Yeah, there's some challenges sort of that go on with this, but let's say that we have some population of rats and sort of they're genetically pure, and so we know on average what this population is going to weigh. And so we have known characteristics of this rat population, right? And so we go through, we don't have access to the population of rats, but we got a good sample of rats. We go through and pull that sample of rats, and then we provide some sort of treatment, right? We do something to those rats. And by doing something to those rats, we've essentially created a new population, a hypothetical population, right? We've still got a sample of that hypothetical population, but now instead of sort of regular rats, we have treated rats, right? And what we can do is we can assume that treated rat population, we're assuming that it sort of reflects sort of if we were to take all rats in this population and inject them with sort of whatever we've done or implemented whatever treatment, we're assuming that would then reflect the characteristics of that new population, that hypothetical population of rats, right? And so what we're doing with our tests is we assume that a population has some specific mean. And what we want to do is we want to think about what's the probability of drawing a sample from that population having a mean of characteristic that we're observing or something that's more extreme, okay? And if we go through and we determine that to be a low probability, right? If we're saying, boy, if this population does have sort of X mean, it would be really unlikely or improbable to randomly pull a sample with these characteristics. What we then do is we would conclude that sort of this population or this sample that we've drawn actually isn't drawn from a population with this parameter, where it's actually probably drawn from a population that has some sort of different parameter. Okay, so in our rat example, right, we know what the population of rats is before they're treated, right? We know sort of the mean weight or sort of whatever it is here, right? But then we go through and we sort of give them some sort of treatment or injection or things like that. Now all of a sudden we've got rats that aren't from the normal population, they're from a different population. We don't know what that population is, right? But we've got a sample of rats from that population because we've created it, right? And so if I know that rats from the normal population should be pulled, have a sort of average weight of 400 grams or something like that. I don't know. Not so great with the metric system. I don't know if that makes any sense, but let's say that it does. And I go through and measure those treated rats. And let's say I get the weight of those treated rats is something that's very different than what I know rats from this population or from the normal population should have. If I'm going through and I find that if the population weight of treated rats is the same as sort of this, if it's 400 grams, and I weigh these rats and it's something that's considerably different than what I would expect, what I would then use with my sort of inference test is the assumption is that, yeah, well, this population from which this sample is drawn doesn't have a mean of 400. It has a mean of something else. My best guess is whatever I've measured sort of this to be, but the probability, if this population of medicated rats actually is 400, it would be very, very unlikely for me to get sort of rats weighing 550 grams or 300 grams or something like that. It would be very unlikely. And so because of that, what I'm going to do is make the assumption that I'm going to reject the null hypothesis that the population mean is 400 and assume that it's something different than that. Okay. So this is the inherent logic of our null hypothesis testing. People kind of following along with this again. So here, as we're talking about, the thing I want you to key on in here, are we ever talking about the sample? Do we care about the sample? Sample is just a means to an end. In terms of hypothesis testing, we're never talking about the sample. We're only trying to infer something about the larger population, which makes it critical that we're identifying what that population is. Who are we studying? Who are we wanting to generalize to? And then that brings in some implications about, is my sample representative of the people who I actually really want to sort of generalize to? Okay. Questions about this? Okay. The other thing too, in terms of when we're talking about hypothesis statements, a lot of times, sometimes we're talking about comparing naturally occurring or naturally existing populations, population this, population that, right? Population of Wyoming versus the population of Colorado. Okay, that's semi kind of existing in that they're already there. I'm not doing anything to sort of create those groups, but a lot of times in sort of experimental and psychological science, a lot of times we're doing something to create like a hypothetical population, right? Like, so let's say, hey, you're doing something, and so you've got a hypothetical population of jury members receiving just regular jury instructions, and then people who are receiving different jury instructions. Now, the only people who got those instructions are maybe the 20 people who you have in that sample, but conceptually, they're representing a hypothetical population of jurors who would receive those, and then how would that population respond? All I have is just sort of the measurements I've got on my sample, but really what I'm talking about is if we were to give this to all possible jurors who could be in juries, what would we expect sort of shift and change to be? That's what we're kind of getting at with this stuff. Okay. Questions about this? All right. So here we've got an example. We've got researchers believe that antioxidant supplements may reduce and possibly reverse age-related cognitive. Those age 65 and older, have them take antioxidant supplements. We then give participants a neurological test to assess cognitive functioning. They're known to be with adults 65 and older, scoring an average of 80 with a standard deviation of 20. Difference in scores exceeding 10 or more points hold practical relevance. Okay. So basically, so we're jazzed about supplements, right? We're like, hey, this antioxidant stuff is great stuff. What we can do is maybe sort of use this to combat age-related cognitive decline. So what we're going to do is we're going to test this in a small study, have 25 older adults take supplements for a period of 6 months, have them come in and measure them and test that against sort of known parameters for performance on this test to see what's happening. Okay. So what we're going to do is we're going to first start with this by stating our hypotheses. Okay. This is predicting characteristics of a to-be collected sample. Okay. Establishing what our null and our alternative hypotheses are going to be. Then we're going to go through, we're going to select a probability criteria for determining what we're going to identify as a reliable or interpretable effect. Okay. Here, then we're going to go through, we're going to collect our sample data, kind of compute our statistics, and then we're going to draw conclusions based on sort of what we found. Okay. These are going to be the same steps that you're going to do for any analyses that you do here. Pretty straightforward. Well, it's not, it gets complicated, but sort of 1,000-yard view in terms of what you're trying to do. This is going to be it every single time. Okay. So first thing we're going to do is we're going to state our hypotheses. Okay. Generally, this involves a couple of related hypotheses. It's probably familiar to stuff that you went through or exposed to in undergraduate statistics. Our null hypotheses is almost always going to be involvement of a zero association between the IV and the DV in the larger population, a zero difference between groups. There's no correlation between these measures again, or these constructs again in the population. The manipulation that we're going to do has no effect on our outcome. Okay. Our null hypothesis is almost always, and will always be for anything we do in this semester, next semester, that the difference between groups is zero, that the association is zero, that it's exactly zero. Okay. If under any circumstances, someone asks you what's the null hypothesis for X, and you don't know the analyses or the statistical model or anything, if you guess that it's probably testing whether or not some value is equal to zero, you're going to be right 99% of the time. Okay. Our alternative hypotheses is we're assuming some non-zero association exists between our independent variable, dependent variable, and the larger population. So we're assuming that the manipulation has some reliable effect on our outcome. Very, very, very important to remember that our null hypothesis, traditional null hypothesis testing is only a test of the null hypothesis. The null hypothesis is the only thing that we're interested in. It's technically the only thing that we're testing. The alternative hypothesis is just there as kind of the other side of the coin. We're never testing the alternative hypotheses. We're only testing the null. Okay. People remember sort of running into this in undergraduate statistics and having this emphasized. Okay. All right. So quick word on statistical models. When we're talking about a statistical model is just a general term. When we think about statistical models, we think about like SEMs and sort of big path analyses and things like that. Really, we break it down to simplest terms. A statistical model is just a set of assumptions that describe how a series of observations might have been generated. Okay. If I am testing sort of mean differences between two groups, I'm saying, well, I'm assuming that I sampled from this population and this population generated the mean observed sample we see for this sample. And I'm assuming I sampled from this other population and the characteristics of that population informed the mean values I'm getting from that sample. And so the reason I'm seeing sort of differences in these samples or the things that I'm actually seeing is because they were generated based on sort of these sample or these populations which I sampled from. Okay. When we're thinking about our null hypothesis testing in routine practice, almost always what we're doing is just looking at a point estimate that's specified within the null hypothesis. So do our data support, I've made a call on expected sort of value of whatever statistic that I'm calculating. Is the data compatible that I'm seeing compatible with that null hypothesis? Okay. And so we're always focused on whether or not something is essentially equal to zero, right? Do we have evidence? Is there evidence to suggest that zero would be a reasonable estimate for sort of what we're getting in, right? But if we actually take a look at sort of what goes into that statistical model, we can think about this as sort of more inclusively as a compound hypothesis that has a whole lot of extra stuff packed into it. Things about, sometimes you'll hear this or see this in the readings referred to as auxiliary hypotheses, auxiliary theories, right? And so all the stuff that we never talk about, but is actually going into the assumption of this model and these analyses, we're assuming that the sample is representative. If the sample is not representative, everything goes out the window, okay? We're assuming that the sample is randomly selected. If the sample is not randomly selected, everything goes out the window. We're assuming that the distribution of sample means is normal. The distribution of sample means isn't normal, everything goes out the window. A model is correctly specified, meaning that sort of the things that need to be in the model are being accounted for, and the things that are extraneous and don't need to be accounted for aren't out. If we haven't done a good job with that, all of a sudden things start to break down. We're assuming our measures are valid, right? We're using strong psychometric instruments and not just something I made up for the purposes of this study. If that doesn't happen, our inferences start to degrade. We're assuming when we get into a lot of these that our measurements are collected without error. Does that ever happen? Nope. Okay. Our hypotheses were generated prior to the evaluation of our data. We would hope that happens, but sometimes it's not. A lot of times, so I sort of do my stuff, and then I'm like, oh, hey, that's pretty slick. Sort of follow up on that piece. That other thing that I thought I was interested in, turns out I'm not. That was dumb, right? What I'm really interested in this thing, right? And as soon as I do that, all those probabilities start to go out the window, right? So if we look at this, folks, when are we when are we sort of have all of these under control? Never, never. It just doesn't happen, right? But this is the vacuum in which all of these procedures were developed, right? And these are the underlying assumptions. Again, we say, oh, the null hypothesis is equal to zero. We sort of really kind of focus on that point estimate, but these are all methodological statistical things that technically, if we want to have the most precise estimates, we're assuming that all of these things are true. But all of these things are never true. And so what does that do to our inference? Grades it, right? It creates additional uncertainty. And so we have to be very, very humble and careful about how we're estimating or sort of the types of inferences that we're making the types of inferences we're drawing from our data. This doesn't mean like we don't ever do anything, but again, what we should do is essentially know where the bodies are buried. Like sort of what are the things that can start to sort of degrade or impact my inferences, and then start to take some of those things into account. Some of these things we're probably okay, and so our models kind of work pretty good if we've done this. Other stuff less so. A lot of this is impacted by generalizability. Who do the results of my study apply to, right? And if my sample isn't representative or randomly selected, I might have to start to be careful about who I think my data generalized to. Some of the other stuff starts to increase error, right? So we start to error in my model, and I start to miss things that I should catch, or maybe find things that aren't actually there. So again, when we're talking about statistical model and assumptions, so long as everybody's playing by the same rules, then we can determine which team is better than which other team, and sort of like on average, who's sort of doing better than what. But as soon as everybody turns into a free for all, everybody's playing by their own rules, it starts to become much more difficult to go through and judge what's happening with things. So we need to be thinking about that methodology and sort of how that goes through and impacts stuff. Okay. Questions about this? All right. So again, the validity of our estimates are all predicated on our underlying assumptions, all these implicit assumptions. We don't talk about them explicitly. We kind of tuck them away and sort of like, oh, let's not think about that because it makes us uncomfortable. It's a whole lot of avoidance, right? That goes into this. But for you, as brilliant, budding, excellent, growing researchers, this should all be in the back of your mind when you're going through and evaluating research. Okay. All right. So for our supplement example, our null hypothesis here is that the mean of our supplement group, mean cognitive functioning supplement group, is going to be equal to 80. Okay. Why? Someone tell me why this is the null hypothesis. Mesa, can you tell me? Like, so why did I specify this as my null hypothesis? It kind of goes back to sort of what did I say was the so in the normal population of older adults, what was the average score on the assessment that I'm giving? It was 80, right? Yeah. So I'm saying the average cognitive functioning score in the population of older adults using herbal supplements is equal to 80. Okay. What does this say about the effect of? What does this imply about the effect of herbal supplements? in the null. If I'm saying the people who have are that would, so if I'm saying, so for people taking older adults using herbal supplements, their score is essentially going to be equal to sort of what we know everybody's is. So what does this imply about the impact of herbal supplements? That there's no change, that herbal supplements don't do anything. So we have created a new population. We've got a population of older adults using herbal supplements. So we've got a hypothetical population of individuals. But what my null hypothesis is saying is that the mean cognitive functioning in those older adults using herbal supplements is the same as the mean cognitive score of everybody. Okay. So essentially we're saying that herbal supplements here have no effect. Okay. And so we've got statistical notation, right? Again, using population-based estimates because we're talking about population stuff. Here we're sort of saying this in a statement. And the big thing here is we're saying sort of like identifying who are we talking about. We're talking about the population of older adults using herbal supplements. That's a pretty broad population, right? We're making a strong sort of assumption on who our data apply to, right? But we're stating it explicitly so it's out there in the open so we're kind of showing all our cards here. Okay. Am I okay if you say the average cognitive functioning score in the sample of population or the sample of individuals using herbal supplements is 80? Do I like that? Why don't I like that, Danielle? I don't care about the sample, right? Do I need a statistical test to tell me if my sample mean is 80? No, I just look at it. If it's 80, then it is. If it's not, it's not, right? I don't need to run a statistical test on the sample. I can just use my eyeballs and look at it, right? But what I'm interested in is, does the information that I have from my sample give me, do I have evidence against the idea that sort of this is coming from a population with mean 80, right? So again, be very careful when you're writing up your population or your hypothesis statements that sort of you're being very careful to specify the population that you're talking about, right? Because this gets into generalization, okay? Our alternative hypotheses here, pretty straightforward, two-tailed test. The mean for my supplement group is not 80. And we say average cognitive functioning in the population of older adults taking herbal supplements is not equal to 80. It's something different, right? We're saying here, what are we saying, Allison, about in this alternative hypothesis? What is this assuming about the impact of supplements? That it has an effect. Are we specifying which effect it has? No, we're just saying it's not 80, right? Does this statement have anything to do with how far away from 80 it is? Nope, just that it's not 80. That's all it is, right? Again, which is fine. We just have to be thinking about what that means in terms of practical implications for our tests. Okay, so we've got our hypothesis down. Step 2, we're going to set our decision criterion here, okay? So what we're doing is sort of what we're wanting to do, take a look and use our statistical methods to obtaining sample data with whatever characteristic we see, assuming that the null hypothesis is true. And what we're going to do is we're going to use that probability to start making inferences about my corresponding population, okay? So assuming that the population of, assuming that older adults taking supplements, assuming that the average cognitive functioning score is 80, what's the likelihood of me getting a sample with these characteristics, assuming that sort of that null hypothesis is true? Okay. If I go through and I find that my sample means are going to be much different from the proposed population mean, right? So the interpretation here is that either that these data are incompatible with the null hypotheses. If my null hypothesis is that older adults taking supplements have a mean cognitive score of 80, and I get this in my sample, I find this, my sample actually ends up after 6 months of supplements that they have a cognitive score of 88, right? That's pretty far away from what I would expect, right? And so if I see that my observed data differ very much from what I would assume under the null hypotheses, I'm either going to say that these data are not compatible with the null hypotheses, like basically that's saying like if the null hypothesis is true, it would be very, very unlikely for me to get a sample with this characteristic, or that these data are incompatible with the assumptions of my underlying model. Do I have a statistical test for this? Nope. This is something I just have to be thinking about and sort of reading into based on on the methodology, okay? Our null hypothesis test doesn't tell us which one of these it is. And it doesn't have to be one or the other. It could be a little bit of both, right? But all it's saying in our null hypothesis testing is that the data that I have collected seem unlikely or are incompatible with what I would expect, assuming that this sample is actually coming from a population with a specified mean. Yeah. Yeah. And this is where our alpha. How much or how far away is too far, right? And so we're going to get that in a moment. Okay. So this is the first thing. And this is kind of always what we're hoping. Data that we get is very different than sort of what we would specify under the null hypothesis, because then this generally allows us to go through and make our sort of inference that, hey, yeah, the characteristics of this population seem to be different than what we had specified under the null, right? But sometimes, most of the time, what's going to happen is our sample mean is relatively similar to the hypothesized mean, right? We don't have much of a difference. I say, you know, my null hypothesis says that the mean cognitive score in older adults taking supplements is 80. And I go through and I sort of sample my, or measure my sample after 6 months of herbal supplements, and I find that they have a score of 82. It's not 80, but it's pretty close, right? What I'm going to do here is probably end up determining that sort of the data that I've collected are sort of relatively compatible with my null hypotheses. They're not identical, but they're at least in the vicinity, right? These data that I've collected, this sample of whatever it is with a score of 82, if I was pulling from a sample with a population, if I was sampling from a population with a mean of 80, I'm going to get samples with the score of 82 sometimes, right? And that's not going to be an uncommon thing. And so what I'm going to do is I'm going to interpret my data relatively compatible with my null hypotheses, okay? So again, the thing to remember is our testing tells us whether the data are unusual, assuming that the null is true. It doesn't apply that any part of the model, it doesn't verify anything. It doesn't confirm anything. It doesn't suggest that I have the right model. The only thing it does is saying, if you say this is what's going on in the population, to what extent is this, the data that I'm observing sort of seem sort of close to that or far from that or usual or typical or unusual, things along these lines. Again, I really like that compatible word, right? Because I seemed consistent with what I would expect, or boy, this is starting to get farther out, right? Now, where we go through and decide where the benchmark is, so how far is farther out? How atypical is atypical? How unlikely do we start to say, boy, this is really evidence that sort of likely this sample was drawn from a population with some value that's different than what we specified under the null, okay? And this is where we go through and set this determined by the investigator. And by the investigator, we mean our science and our field. Like, it's really not up to you what your alpha criterion is. I mean, it is, but if you say like my alpha is 0.25, like you're probably not going to get far with that, right? Our standards is 0.05, right? And this is going to go through, and this alpha level is going to be used to define our critical regions that are going to start through and thinking my curve, like how far out there do I get before I start to say, boy, these data are really incompatible with what I would expect, given everything I know about, or given what I've specified under the null hypothesis, okay? And again, this alpha level, these are going to be our benchmarks for setting. If I were to collect a sample that falls in this probability level, sort of an either tail, this is where I'm going to start saying, this is my goalpost for saying, yeah, these data are unlikely. And so I'm going to say, likely sort of reject the null hypothesis and say, if this is the null hypothesis were true, formally, this is an unlikely result to get. Okay. So again, for my supplement sample, so this is the distribution of sample means, assuming the null hypothesis is true, right? If the population mean cognitive functioning score in older adults taking supplements is actually 80, right? This is what I would expect in terms of my sampling distribution. And what I'm doing is I'm going to start to set a critical region. We're going to say it, call it alpha equal 0.05. This is just based on convention. These are our benchmarks. So if I get a statistic that falls beyond this, this is my threshold, my trigger decision to say, yes, I have evidence for this effect, right? If it falls in this region, if it falls in that region, then I'm saying I have evidence for an effect. If it, well, it's not the same, but it's generally compatible with what I would expect based on sort of the assumed distribution of these scores. Following this along? Yeah, Mandy. What's that now? No, I will one never say that the null is true. There's nothing I can do that sort of tells me that the null is true, right? I just say, are my data my data consistent or compatible with the null hypothesis, or do they seem inconsistent with the null hypothesis? The null, if we're in here, if we're in the body, does anybody else see that screen is flashing? Yeah, that's really bothering me. Yeah, I'm like, yeah, no, I throw myself into a seizure here. But yeah, so if we've got compatible with the null, I mean, and so and as they get closer and closer to the edge, they get less and less compatible. We're just sort of making a yes no decision that this is where this is falling. If we're in the critical region, that's where things are going to be, where that these seem to be incompatible. Yeah. Yep. Yep. And this is where we're going sort of based on that yes no decision. And that's been the tradition in our field, but as we're going to get into, there's sort of creates a lot of problems when we're starting to sort of make that yes no decision. So yeah. Yeah. Yep, exactly. And you're going to see like, I notice that I've not sort of minimized sort of my reference to significant anything. We're going to talk about sort of the history of that language and how that's sort of led to some problematic stuff and all the reasons why that starts to become probably not an optimal way to go through and think about things. Yeah, Jalen. We'll get into that in a little bit. So basically, yeah, hold on to that. We'll get into that in terms of thinking the one-tailed to the two-tailed. Yeah. Mm-hmm. Almost. We can never prove anything. So, and again, this starts to get into a little bit semantics and it's kind of tricky. All we can do is say that our data are sort of seem to data are sort of seem fairly compatible with the null hypothesis, or if the null hypotheses were true, then these data sort of seem pretty reasonable, or these data are very improbable, assuming that the null hypothesis is true. When we start to get into things like prove, again, that starts to get into yes, no decisions, like either approved it or I didn't, right? Well, again, remember we talked about like one study tells us very, very, very little about a phenomenon. Like we can have very good studies that maybe are real well constructed and sort of give us maybe a strong suggestion that maybe something is going on, but it's only with repeated assessment and replication and stuff like that where we start to have strong evidence for something, right? Now, like for my own area, if you ask me, are measures of post-traumatic stress disorder associated with measures of social support? I would say, yeah, I think that at this point, the literature is, I wouldn't use this word, but yeah, I could say have proven that there's an association between measures of social support and measures of PTSD. But that's only because there's been about 1 billion studies have estimated that, and sort of estimates vary widely. But if we go through and look at meta-analyses, we can start to say like it's probably about something like this. But if I'm doing novel research that no one's ever looked at, sort of this specific association before, this specific model or anything like that, things are suggestive and can be consistent with sort of theory and conceptual models and things like that. But we want to be very, very careful and never use, because we can't prove anything, right? It's sort of for experimental folks, it's kind of the same, put that in the same category as starting to talk about causal relations between things, right? Like just the level of evidence in order to make that claim is so high, we just sort of assume, right? Now that differs from sort of a discipline to discipline, but it's one of those things. So we never proved that none of data are consistent with the null, or we reject the null, or we fail to reject the null in traditional terms. Does that help? No, probably not. Probably fail to reject for a lot of different reasons. A lot of it is that they're just like the things that we think should happen actually don't most of the time. So, welcome to my research program. And then just because of power and design issues, like this really gets, and we're going to get into this sort of a really interesting philosophical debate about sort of what our method is and what it tells us, and sort of what the types of inferences that we can get. So hold on to that, Mandy. Okay. All right. So we've set our alpha levels, and so it's been forced upon us because we're all in a joint endeavor called psychological science, and we're sort of go through, call that alpha 0.05. And so then what we're going to do in our most basic scenario, we're going to calculate sample statistics and compare it to known population parameters. Okay. In this example, we have sampled from a hypothetical population of older adults who are taking supplements. We don't know what that population value is in terms of mean cognition, but we do know in this hypothetical scenario what the mean value on this cognitive test is for older adults in general. Okay, so I've got a population parameter that I can compare against. And so what I'm going to do is I'm going to calculate a confidence bound for my mean estimate and sort of upper and lower limits of data supported values for what my estimate is. And then statistic z-score in this situation that's going to locate the position of my sample mean relative to the known population mean based on the null hypotheses. Okay, and again, this is just my z-test here. It's calculated as my sample mean minus the population mean over the standard error. Standard error, again, is just the standard deviation divided by the square root of the sample size. Okay, or like those back test, or sort of mathematically equivalent. Here, got a variance estimate. Then you just the yeah. So what we're doing is my sample mean divided by my statistic, and then I'm looking at sort of calculating the standard error there. Again, remember I was sort of talking about like sort of take an intuitive look at sort of these ratios and what they represent, right? Hopefully the z-test isn't just like, okay, these are the steps that I plug in. If I actually look at this, it's telling me information about what I'm actually trying to do and sort of what's happening with this test. The numerator here, we have the observed difference between my sample mean and my null hypothesis, or in the value under the null, okay? This is the discrepancy I'm seeing between my presumed population value and what I'm observing in my sample. So we've got a deviation score here. And then down here at the bottom with my standard error, this is telling me the expected distance between a randomly selected sample mean and the population mean under the null hypothesis. So I've got a sort of a measure of the distance between what I assume is true under the null hypothesis and what I've actually observed. And then the denominator is telling me, assuming that the null hypothesis is true, how much should I expect scores to jump around from, differ from the mean on average. So if I get, Allison, if I find that I expect on average, based on my sample and the characteristics, that my sample mean, just randomly selected sample mean should jump around very little, and I actually observe something that's quite a big difference between my observed value under the null and my actual sample mean, what's going to happen to my z-score? Going to be bigger, and what's going to do to the likelihood of me rejecting the null hypothesis? Like some triple negative stuff like that. Yeah. So as my z-score gets bigger, what's the likelihood of me finding an effect or concluding that I found an effect? My z-score goes up. More likely. we're talking about the absolute value of the z-score, right? Because we've got a two-tailed test, right? Correspondingly, let's say that, so here, I expect, given the characteristics of my sample, I expect any randomly selected mean to kind of jump around quite a bit. And I do find a difference between my sample statistic and my presumed population parameter. But it's kind of within what I would expect. What am I likely to do in that scenario? What's going to happen to my z-score? Going to go down, and I'm less likelihood to conclude. In fact, I'm probably going to reject or fail to reject the null hypothesis in that situation, right? So again, looking at that ratio, it's just a distance of the difference that I've observed over the difference I expect based on just random fluctuation. If that ratio starts to get really large, I'm more likely to claim an effect. If that ratio gets close to 1 or is very, very small, then I'm probably not, right? So again, looking at these formula and sort of understanding conceptually what's going on, as opposed to just sort of like ignoring them and sort of thinking about these as something that I plug values into, will help with the conceptualization. And then also if you've got, like for the midterm, a big ass sheet of formulas, right? And it's basically just notes in statistical notation. Like, this is what this one is doing. This is what this one is doing. This is what this one is doing. This can be super helpful. So don't be afraid of. A couple of so looking at the Z statistic, examples of 25, scored an average of 92 points on our neurological assessment. Again, assuming that in the population of older adults, so this has been normed, we know that it has a mean of 80 and a standard deviation of 20. Okay. So again, if I'm going through and writing this out, so I've got me, I've documented this is just how I'm setting things up, right? So I've got, okay, and I'm going to go through and calculate my standard error based on, because I've got a known population value. Gives me my standard error of 4. Okay. Yeah. Yeah. You write it down, take a picture, do whatever you want. This will also be on sort of on the video that we're recording too. So if you don't get it, so oh, is that okay? Okay, so yeah, so to write this down, so on notes, however you're taking it and things like that. But yeah, absolutely, yeah, there's nothing proprietary in this. But if we're thinking about this, Daniela, what is this value of conceptually? I got a standard error of 4. How can I interpret that?